Hi, this is Jason Baker, and welcome back to our lecture. In the previous segment, I talked about servers having a life cycle. You can create a server, launch a new server, and then you might update the server over time, and eventually you might terminate that server and replace it with a new EC2 instance. Well, we covered in the previous section how you might go about creating a new server using a template, and you can use a tool like Packer to automate the building of an AMI in EC2. Well, how do you go about updating a server over time? So you launch a server and it's running your software and configuration, but maybe you need to make an update to the system. Maybe you need to change the configuration. Maybe you need to apply a new version of some software service that's running on the system. There's a couple different ways you can go about updating a server. And in this lecture, I talk about four different models that you can follow to make changes to servers. The first way to update a server is to make ad hoc changes, which means that the server is up and running, and at some point you decide that a specific change needs to be made to the server. So you manually shell into the server and then run the necessary commands to update the system. Maybe you're updating, installing new software, or you're changing the configuration of a service. You're doing this on an ad hoc basis or on an as needed basis. Well, the problem with ad hoc change management is that it tends to leave servers inconsistently configured over time. Imagine you have like 10 different web servers and you're making ad hoc changes to these servers. Well, after a period of time, the server configurations are just simply going to drift apart. And that's something that we call configuration drift. So you have this set of 10 web servers that were all configured identically initially, but then over time, the configurations of these servers kind of drifted apart as ad hoc changes were made to the servers. This ad hoc change management is a process that I still see very commonly used by organizations. And it's really a poor way to manage the configuration of systems. It introduces quite a bit of risk because of the configuration drift that results from these ad hoc changes. Another way to manage the configuration of servers is to continuously synchronize the configuration of servers with some sort of centralized configuration management system. So you have this, think of this centralized system that describes how servers should be configured. And so this centralized system is continuously synchronizing and updating the configuration of servers in an environment. And it might do this on an unattended schedule. So like every 30 minutes, each one of the servers in your environment is checking in with the centralized configuration management server to see if there are any configuration changes that need to be made. One of the benefits of this practice is that the centralized configuration management server can validate that the configuration of the servers is still correct. And if somebody went in and made an ad hoc change to a server, then that would be detected, and that change then would be reverted, and the intended configuration or the desired configuration would be reapplied to the system. So the way you think about it is that you define a desired configuration state, and then you have this tool which is constantly, synchronizing all the servers and ensuring that the servers in your environment are running the desired configuration. And this helps to minimize configuration drift to a great extent. It doesn't totally eliminate it because, well, these sort of centralized configuration management systems don't necessarily control all of the configuration of a particular server. They might only be focused on, part of the configuration of the server. So there's still an opportunity for the components on the server which are not being managed by a configuration management system to experience configuration drift over time. A third model that we could follow to update our servers is what we call the immutable server model. And an immutable server model, instead of trying to update our servers, we just simply replace them. This kind of relates back to that pets versus cattle analogy. And if you're sort of maintaining your servers over time and you're updating them over time, you're sort of treating them like pets. Well, instead of treating them like pets, we can just simply replace them whenever we need to. And then we replace them with a server that has an updated template and that has all of our updated software and configuration in place. The big benefit of the immutable server deployment methodology is that we don't have to deal with all the unexpected challenges associated with trying to update an existing server. Sometimes software updates just don't go very well. So instead of trying to update the server, we just simply replace it outright. And it also mitigates configuration drift because instead of updating our servers sort of continuously, we're replacing them continuously. So servers really don't have a chance to drift apart from a configuration perspective. One way to implement this immutable server deployment pattern is to follow something called the Phoenix server pattern. And with the Phoenix server pattern, you don't replace servers when you want to make a change. You replace servers on a scheduled basis, regardless of whether or not you need to make a change to the server. For example, you might decide that you're going to replace all of your servers once a week, or maybe even once a day. And so every server is kind of like a fresh system, a new system. The Phoenix server pattern is fairly common. It's really common in organizations that are using virtual desktops. You'll see that like these companies provide a virtual desktop to their employees, and then like every day that virtual desktop is completely wiped away, and a new one is created, a new fresh one is created. And then the fourth server update pattern is to utilize containerized servers. And with containerized servers, we're basically packaging applications and all the dependencies of those applications into a container. And we're essentially then updating the container over time. We're essentially replacing the container with a new one. So this is very similar to the immutable server pattern, but instead of replacing a server, we're replacing a container. And we'll learn a lot more about containers in a few weeks. So let's review once again some of the challenges that we encounter when we're dealing with dynamic infrastructure. And this is, cloud-based infrastructure that we build using an infrastructure definition tool. Well, one of the challenges that we can experience with dynamic infrastructure is server sprawl. It's really, really easy to provision new servers in the cloud. And I see this happen all the time when companies are first beginning to deploy infrastructure in the cloud. They start out by deploying maybe a couple dozen EC2 instances, and then before you know it, 6 months later, they suddenly have hundreds of instances. And oftentimes it's because they're not practicing very good hygiene in their environment. They're not reaping old servers. They're not replacing old systems, and so they're leaving a lot of old EC2 instances needlessly running in their environment. I talked about configuration drift. If you have lots of servers in your environment, and if you're trying to make updates to those servers over time, then gradually the configuration of these servers will sort of drift apart, um, and and then that can lead to something that we call snowflake servers. Snowflake servers are these unique servers in our environment. These are pets, and these are servers that are not easily replicated. These are servers that nobody really understands how they were configured, or maybe even what they're doing anymore. But they know that the Snowflake server is somehow involved in say some sort of important process, and people are too afraid to do anything with that server because they don't want to break some important service. You want to try to eliminate Snowflake servers in your environment as much as possible. Over time, what you might encounter is something that we call automation fear. And I've seen this with organizations where, you know, we all know how important automation is when it comes to, just building and defining our infrastructure. And it's absolutely critical in order to scale our processes successfully and make them reliable and repeatable. What you'll find sometimes is that in organizations where they've traditionally made changes to servers on an ad hoc basis, and where much of their infrastructure is sort of built by hand, I call it hand cranked infrastructure, you'll find that these organizations are often very fearful of running automation tools. And that's just simply because um, it, it's because so much of their environment is sort of manually built and manually tailored, and the automation tools, might cause them some problems. Um, the the way to really mitigate that, I think, is to in some cases rebuild the infrastructure, and rebuild it using an infrastructure definition tool, and start using tools like Packer and Ansible and others to manage the configuration of services. And you don't necessarily have to automate everything initially, but you start with at least one part of your infrastructure, and automate that piece, and then begin automating other parts of your infrastructure as well. And then finally, dynamic infrastructure environments experience what we call erosion. And that's this notion that there's this natural entropy which um, sort of creeps into our environments and sort of naturally causes problems to begin to appear over time. If you launched, let's say, an EC2 instance, and you let that EC2 instance run for months and months and months, over time, sort of like this natural entropy will begin to maybe degrade the performance of that server. And it's due to a whole variety of different reasons. It could be software bugs, or things like memory or buffer overflows. It could be log files beginning to fill up storage volumes. Our systems just kind of naturally become less dependable over time. The performance of our systems erodes. And the way we mitigate that is by is by replacing our systems and maybe using an immutable infrastructure model where we don't let our servers run for months and months and months. We replace them on a periodic basis with new, fresh instances. Okay, so we looked at the variety of ways that we can upgrade the configuration on servers. And I wanted to dive a little bit into the continuous synchronization pattern. And this is a pattern whereby we can update the configuration of a server by running a tool and using a process which will kind of continuously manage the configuration and ensure that the configuration of a server meets a desired state. And there's sort of three different ways that we can synchronize the configuration of a server. One way is that we can use this sort of master server. Think of it as a centralized server, which is pushing out configuration updates to other servers in our environment. It might communicate with the other servers via something like SSH, and so this centralized server is shelling into all the other servers in our environment, and then once it's shelled into those servers, it's deploying configuration. It's deploying new software. It's running certain configuration commands. Another way we can synchronize the configuration is by pulling the configuration. So each server that's running in our environment might be running a configuration management agent. This is a special piece of software. And this agent could reach out to a centralized configuration management server and pull the desired configuration from that server and then apply that configuration in the local server environment. And then the third way to synchronize the configuration of a server is what we call a masterless configuration management process. And with a masterless configuration management process, there is no centralized configuration management server. Each individual server in our environment will basically download essentially like a template, a configuration template. And then the server will run a software tool on itself, essentially, and it will apply that configuration template. And that configuration template then will install software and run various commands. The benefit of the masterless configuration management pattern is that there is no centralized server that you have to maintain. There's no centralized server that might be a bottleneck. If you have like hundreds or thousands of servers in your environment and they're all trying to synchronize with a centralized configuration management server, that could potentially be a problem. Okay, so let's look at a tool that's commonly used in the marketplace to manage the configuration of servers, and that tool is called Ansible. Ansible is a free software tool that you can use to manage your server configuration. It's primarily used as a push-based tool, meaning that you can install Ansible on your laptop, you can install Ansible on another server, and then you can use Ansible to manage the configuration on other servers within your environment. And the way that Ansible does that is that Ansible will shell into a remote server, and then it will run all the commands necessary to install and manage the configuration of software. You can run Ansible as an ad hoc command, so you can like literally go to the command line and run Ansible and have it run a configuration command against some remote server. You can also create a sort of a template file that is called a playbook. And this template file is written in YAML, and you can use the YAML code to describe how Ansible should configure a particular system. Now, Ansible itself is written in the Python programming language, and it was originally written by Michael DeHaan, and a few years ago was acquired by Red Hat. And Red Hat has built a number of commercial tools around Ansible. You can go and download Ansible at www.ansible.com, and it will run on both Linux and on Windows systems. Here's a kind of an overview of the Ansible architecture. So Ansible it uses a number of different components to configure remote systems. So you're here as a user and you can run the Ansible software. When you run Ansible, you oftentimes you are executing an Ansible playbook, and that Ansible playbook is this YAML configuration file. Ansible will use that configuration file then to manage the configuration of servers within your environment. And it does that using a couple different components. Ansible maintains an inventory of the servers within your environment. So it knows which playbooks to apply to which hosts in your environment. You might have an Ansible playbook that describes how to configure a web server. You might have an Ansible playbook that describes how to configure a database server. And the web server and the database server would be stored in the Ansible inventory. Ansible also uses modules, and modules are really what makes Ansible a very powerful tool. So these modules are like small applications which Ansible uses to perform different configuration tasks on servers. For example, if Ansible needs to install a software package on a server, it can use a yum module. If it needs to start a service on a server, it can use a service module. And there are hundreds and hundreds of different modules available that you can use within your playbooks, and we'll see more of that here soon. And then finally, Ansible has an API that we can leverage, and it has plugins that we can leverage to extend the functionality of the Ansible platform even further. I mentioned that Ansible uses playbooks, and playbooks are Ansible's configuration, deployment, and orchestration language. They're written in YAML code format, and these YAML files basically describe the configuration state of a system that Ansible is managing. Now, when you create a playbook, and again, the playbook is a YAML file, each playbook is going to contain one or more plays. You can think of a play as a set of tasks that you want Ansible to perform. And the set of tasks are usually related to a particular goal. Like, for example, you might want to install and configure a web server on a server. And so you might create a play which describes how to go about installing and configuring the Nginx web server on a server that Ansible is managing. So playbooks contain plays, and each play is going to contain one or more tasks. Think of the tasks as being the individual steps. So, like, if you think about, well, how would you go about installing and configuring Nginx on a server? There would be a series of tasks that you would need to perform, a series of steps that you need to perform. Each task is going to call a module. And think of the module as like a helper application. The module is actually going to be doing the work. It's going to be installing software, configuring a template for or configuration file for a service. It's going to be starting a service, and so on. Now, all of these tasks and plays that you define within a playbook are run sequentially from the very top to the very bottom. There are special tasks that you might encounter within playbooks that are called handlers. And handlers are tasks that may be triggered by other tasks in a playbook. And a handler is something that is going to be run only once after a play ends. So for example, you might have a play which describes how to build and install an Nginx web server. And then you might have a handler that is triggered by that play, and the handler might automatically start the Nginx service. Here's a quick example of a playbook. Again, this is a YAML file, and we can see that because it starts with the 3 dashes to the very first line of the file. And then we see in this case, a single play. So each play is basically an array member or list member within the YAML document. So this play we give it a name, which is install and start Apache. It's going to be run against the web hosts in our inventory, and we provide it with some user credentials that Ansible will use to log into that server to run the configuration tasks. We can define some variables, and these variables are used within the playbook. And then finally, we describe tasks. And this is a list. You can see a list of tasks. So in YAML, each list item begins with a dash. And so each task has a name. For example, install HTTPD, which is Apache. And then the task is calling a module. In this case, we're calling the yum module. And the yum module is going to install the HTTPD package, and it's going to install the latest version of that package. And then there are other tasks here. And then finally, you see there's a handler. And this handler is going to be then triggered by the service. So it's going to ensure that this service is restarted. And so here's the handler being triggered. You see this notify element is going to trigger after this task runs. It's going to trigger this notify, and then after all of these tasks in this play finish, this handler, because it was triggered, then will execute after the play finishes. Don't worry if this isn't making a whole lot of sense right now. We'll go through each one of these different configuration elements in more detail here shortly. I mentioned that Ansible uses an inventory, and it uses an inventory file, which is typically named the hosts file. And the hosts file contains a list of systems that Ansible will manage. The hosts file it uses an INI type format. An INI file is a file format that was popularized by Windows and other systems. So you look at this hosts file, you see that there are two groups, one called web servers, one called databases. And in the web servers group, we can find two web servers defined. One is called web1, and the other one is called web2.mydomain.com. And for each server that's defined, there are a number of attributes that are also defined. So for example, web1 is located at this IP address, and Ansible will use this user account to log into the web1 server. The web2 server has a fully qualified domain name, so Ansible will just use the fully qualified domain name to access the server. On the database on the databases group, we see a database defined, except this is really an expansion sort of attribute here. So what this is really defining is database servers 01 through 010. So think of this as being like a list of 10 database server instances. This is sort of a shortcut way of describing the set of 10 database server instances. And they're all located at mydomain.com. And this is a variable that's being set up that will be passed by Ansible into a playbook when managing the configuration of these servers. One thing to note is that you can have multiple groups of servers defined in the inventory file, and these hosts can be members of one or more groups. So it's possible for, you might have a server that's both a web server and a database server. Maybe it's running Nginx and it's running MySQL. So it might be associated with both groups. That's perfectly possible. You can define variables in your inventory files, and then you can pass these variables into the host when you're configuring them. That's a way you can sort of parameterize playbooks, and you can sort of dynamically inject different values into the playbook when it's run on a particular instance. There's a variety of ways that you can pass variables into Ansible. You can also define a variable, a file, which is a YAML file in Ansible that contains key value pairs, and Ansible can use those key value pairs and to define variables as well. Okay, so Ansible itself is a software tool, and Ansible has its own configuration file, and you can use this configuration file to control different software settings within Ansible. So Ansible, it'll work typically just fine right out of the box, so to speak. But you can tweak the values in the configuration file if you need to override some of the default settings. And Ansible looks for a configuration, its configuration file in a variety of different places in the operating system environment. If you could define an Ansible config environment variable, which points to the location of the configuration file. Ansible will look to see if there's a file called ansible.config in the current working directory. It'll look for a .ansible.config in your home directory. And then finally, it will look for a file called ansible.config in the etc ansible.config file. So the variety of different places that you can put this configuration file on a system. And you don't really need to be too concerned about this configuration file in this class. In the environments that you spin up where you'll be using Ansible, the configuration file is already set up properly. I just want you to be aware of the fact that there is a configuration file for Ansible, and that there might be if you're using it for your own environment, your corporate environment, chances are you'll need to modify some of the configuration settings in that file. Probably the most important setting in that file is a setting that describes where the inventory file is located on the system. So Ansible needs to know where that inventory file is on your system. Now, when Ansible is applying configuration to systems, it looks in the inventory file to try to figure out, which systems it should apply a particular configuration to. If I go back to this example playbook, you'll see that this example playbook is running a play, and it's going to run that play against the web the web group in our inventory file. So every single server that is a member of the web group, in this case here it's called web servers, but pretend this was just web. Every single Ansible would run the configuration and apply that configuration against every member of the web group in the inventory file. Now, you can control which servers the Ansible is going to apply configuration against. And there's a number of different ways to do that. You can use different patterns to describe which groups or which hosts Ansible is going to apply configuration against. You could create a play which is going to apply configuration against every host in the inventory file, in which case you can use the word all, and that will Ansible then will apply the configuration against all hosts. You could also use just the asterisk character as a wildcard character. You could tell Ansible that you want to apply configuration against all hosts that with a name that ends with .com by using star.com. You could tell Ansible that you want to run configuration against a single host, and you explicitly specify the host name. And then there's a variety of other patterns, and this is a kind of a limited set. There are really like dozens of different patterns that you can use, but like you could tell Ansible that you want to apply configuration against web servers or database servers. You could say I want to apply configuration against all the web servers except for the web 1 server. Or I want to apply configuration to all of the servers which are members of both the web servers group and the MPLS, the Minneapolis group. So lots of different host selection patterns that you can use with Ansible. Now, when Ansible is applying configuration to servers, it's doing so using modules, and these modules are these like little helper applications that Ansible can use to automate every part of your server configuration. There's hundreds and hundreds of different modules that are available to you. And of course, you can create your own modules if you find that there's one that doesn't exist that that you need. I've never had to create my own module. I've always found that somebody else had already done the hard work for me. So when you're using modules, you're basically passing in directives, or another way to think of it is you're passing in arguments to a module, and that is it's like you're running a command. Think of it as like you're running almost like a shell command, and you're passing in arguments to that command. the module that will then, based on those arguments, will run a certain way. So here's the typical structure that you'll see within a playbook when we're referencing a module. You'll see that we call a module name, so we use module colon, and then a series of directives. And the directives are generally like key value pairs. And these directive key value pairs are passed into the module, and the module will run a certain way based upon what directives we pass into it. One other thing I should note is that you can, of course, create playbooks, and playbooks will we use playbooks to build and manage the configuration of servers. You can also create something called a role, and a role is a way to sort of abstract the configuration of a server even further. You can think of a role as being um, a role is oftentimes comprised of multiple playbooks, and we use roles to essentially create a reusable configuration pattern within our environment. So, for example, we might have a web application server role in our environment, and the web application server role describes not only how to it describes sort of like every different configuration element of a web application server. And so then we can use this role as this sort of like reusable playbook that to stamp out other web application servers within our environment. We don't use roles in this course because it's more of an advanced concept. So I just want you to be aware of the fact that that this sort of more generalized role abstraction layer is available.